Good morning. It's wonderful to hear all the buzz and the discussion and the conversation going on, and I'm sure 90% of that is about the Nobel Conference at Gustavus, the 49th. Isn't it exciting? It's again my honor and my privilege to welcome you to this second day of the Nobel Conference at Gustavus. We certainly had a wonderful day yesterday, and I especially want to thank Dr. Wilczek, Dr. Shears, Dr. Filippenko, Dr. Tang, and for their lectures and for their insights into the universe at its limits. I hope many of you were able also to visit the Nobel Conference art exhibit in the Hillstrom Museum. If you haven't had a chance to do that, I think you will want to do that. The paintings done by Lucinda Mason shortly before her sudden death, in which she sought to explore the micro and the macro elements of the world, asking, can one paint the essential makeup of energy or the immeasurable space? I also want to publicly thank the conductor and the wind orchestra who performed yesterday's prelude, and also the Vasa Wind Orchestra and the conductor who performed the prelude before our afternoon sessions yesterday. And finally, regarding yesterday's program, I hope you had an opportunity to go to the concert last night and hear from three outstanding Gustavus faculty. Weren't they great? Violinist Jill Olson-Moser, cellist Sharon Montner-Rogers, and pianist Yumiko Yoshima Ryan. We are so fortunate to have talent across the campus in so many different ways, and the faculty are engaging not only their students but the entire public. As we begin the program for today, I again want to thank the Gustavus Symphony Orchestra this time and their conductor for the wonderful opening music we just heard. We look forward to Dr. Smoot's lecture this morning and to Dr. Krause's lecture and to Reverend George Coyne's talk this afternoon. And I hope you've scheduled time to permit yourself to stay for the closing discussion done by Dr. James Gates. And as you heard, Dr. Gates has been a presenter here at the Nobel Conference before. He is now serving as the Rydell professor for us and is spending time this year on campus coming back and forth to visit with our students. We are certainly so pleased that the students that are here again today with the program that we discussed, please greet them as they stand in the balconies. Please, students, stand. I just talked to a young man, 14 years old, who had an opportunity yesterday to watch the streaming of the lectures. He's seated right over here. And he is a 14-year-old who is extremely excited about physics. And I said to Dr. Niederreiter, how wonderful that must be for you as a scientist. And I say to our presenters, for a young man to make a call last night to see if he could get a ticket to come. And so he's here to enjoy this firsthand. Again, thank you. Again, I call your attention to the sponsors of the 2013 Nobel Conference. It is important that we have companies and individuals who support this to keep it going, and that we have the permanent endowment. As I mentioned yesterday, this is an exciting time for liberal arts education at an institution like Gustavus Adolphus College. The Nobel Conference at Gustavus enables us to share with our students and our faculty and hundreds and thousands of people here in Minnesota and across the country and around the world exciting, cutting-edge theory and important scientific issues. It has been our joy to have you here for the last 2 days. I know we're in for a great day today. I now introduce Dr. Chuck Niederreiter to come up so that he can say a few words and then start the program by having the first lecture introduced. Chuck?
Good morning. Welcome, or welcome back, as the case may be. I hope that you had as much fun yesterday as I did. We had 4 awesome talks, a great concert, and some people even made it to the observatory last night. I hope that you're not too tired to enjoy today's festivities, though, because we have 4 more great speakers lined up, and we'll get started in just a moment. As I was still reflecting on the conversation we had after Professor Ting's talk last night about science education, I watched the group of students and faculty from Stevens Point assemble in front of the stage here for a picture, and I was reminded that not all is bad. They are one of several large groups of young people that attend the conference each year. In their case, as is true in some of the other cases as well, the students paid their own way to learn more about science and learn how science is done. Another group that comes to the conference every year is the intergenerational group from the Appleton area. We applaud all of the organizers for making the opportunity available to so many students and adults. Thank you. I want to give a little shout out this morning to the college groups joining us over the internet, like the group at Hobart and William Smith College in Geneva, New York, that is. Thanks also to the organizers of all of our off-campus venues. And before we get started, I want to remind folks about the exhibits that we have over in the blue side of the forum. If you haven't been over there, there's an opportunity to go inside the Explorer Dome or to check out the demos that Alan Lipke brought down from the Sudan mine so we can learn more about neutrino physics. So at this point, it is my honor to introduce one of my newest colleagues in physics, Professor Jesse Petrika, to introduce Professor Smoot.
Good morning. It's my pleasure to introduce our first speaker of the morning, Dr. George Smoot III, Professor of Physics at the University of Paris, Diderot, and the University of California, Berkeley. I'm going to ad-lib a little bit here. George wanted me to keep my comments short, but after meeting George and all of our other speakers, I just wanted to say thank you for the wonderful opportunity that we've had. Our speakers are so generous with our students, with our professors and our faculty, and with the other people that they've met around the conference. So thank you very much. As I continue, so far our speakers have explored the limits of the universe from a number of different dimensions: small and large, matter and energy, known and unknown. Everywhere we look, there are bridges between these limits. But there are yet other dimensions of this universe for us to explore. Just yesterday, we heard from our speaker, Dr. Filipenko, how he used measurements of the sky to tell us of the ultimate fate of the universe into the distant future. It is now time for us to use the sky to survey the universe's past. Humankind's vision of their place in the universe has evolved remarkably from a heavens above Earth at the center of the universe to living on one of many planets, an indistinct portion of the cosmos. This vision has changed in the last 2,000 years plus because of our ability to map the universe in different wavelengths and to better precision. Or to paraphrase our next speaker, to go anywhere and to do what is necessary to pursue the truth. Dr. Smoot has a truly distinguished career in this endeavor and joins us to share his work. Where are we? Oh, missed one slide there. Dr. Smoot grew up in a family where the value of education, the joy of exploration, and the potential of science was evident early and often. Throughout his childhood, his parents continued their own education, his mother to become a teacher and his father to become an engineer. Their examples led Dr. Smoot to study hard and to read new subjects vigorously. So too, time spent living in remote Alaska and later observing his father lead Expeditions to places like the Amazon and Mekong rivers led George to be adventurous and to be a risk taker. Finally, all this was enveloped in the language of science, as this was his mother's teaching subject, and his father's work was as a hydrologist for the United States Geological Survey. This led Dr. Smoot towards science. Dr. Smoot enrolled in the Massachusetts Institute of Technology, where he was drawn to the subjects of mathematics and physics. He earned his BS in both of these subjects in 1966, but chose to continue in particle physics at MIT, where he earned his Ph.D. in 1970. In 1971, he moved to the University of California, Berkeley, where he soon started to work on astrophysical questions related to the verification of the emergent theory known as the Big Bang. Since then, Dr. Smoot has spanned a number of experimental efforts at mapping the sky. One of these efforts, the COBE mission, which I detailed yesterday, found evidence for the density fluctuations in the early universe that were precursors to the large galactic clusters we see today. When he presented this data publicly for the first time, his assertion that, quote, "If you're religious, it's like seeing God," summed up the sheer magnitude of the discovery and its importance in what is now called the standard cosmological model. From studying the Big Bang to appearing on the TV show of the same name, Professor Smoot believes that it's important to be a role model for young scientists and the general public, as I alluded to earlier. Thus, he also appeared on the quiz show, Are You Smarter Than a Fifth Grader?, winning the $1 million while proving scientists can still be cool with the kids. For the older kids, like our aspirational physics majors who dream of doing astrophysics on the level of Dr. Smoot, he founded the Berkeley Center for Cosmological Physics. Professor Smoot has a long list of accolades and prizes, including the 2006 Nobel, for which we honored him yesterday. Truly, he goes where and does what is necessary in the pursuit of knowledge. Please welcome Dr. George Smoot to Gustavus as he gives his talk entitled Mapping the Universe and Its History, and helps us do the same.
Thank you. It's a pleasure and honor to be here, and it's always exciting to see, interested students in a place that's not yours. It's good in your own place, but it's so much easier. It's like having grandkids to come to students at another place. So, but I commend Gustavus for having tremendous collegiality and tremendous, sort of esprit de corps for the whole college, faculty and the students. And the bringing in of high school students just continues that along the way. And as we said yesterday, I think it's very important for people to value education and to value the sciences as part of that education. So I am giving a talk. You will find some of these slides have been taken from other talks and other places. So this talk I'm going to give today, I give the title Map of the Universe, or Map of the Universe and Its History. And but what we're trying to do, you'll see, is understand where the universe came from and how it's developed over time. And so it's another thing that you may recognize is the Cosmic Scene Investigation, CSI. You notice the fingerprint, the ghostly fingerprint in the background. It's the similar kind of thing that we do as cosmologists that the forensic scientists do when they try and reconstruct from flimsy pieces of evidence what happened at a crime and make it conclusive. And we use a lot of the same techniques, including the computer simulations and the gathering of data and making of models and putting things together. And we're trying to do it. The crime we're trying to reconstruct is the universe, so it's a little bit different. And what do we mean by that? I mean, if you're a cosmologist, your job is to explain everything. That is, why everything in this room is here. And it turns out you can make a lot of progress. One of the things that I do is I've come to admire Boltzmann very much because he made the first laws of physics that were actually statistical. And so my standards are, if I can describe the universe really accurately statistically, then that's pretty good. I don't have to describe every detail, like why the E equals mc squared is missing the 2 a little bit here, cut off by the, I don't have to explain all those details. I need to explain the big features of the universe. So part of the evidence is in this room. And in fact, you'll see we can explain a lot of what's in this room, although I won't cover all that in this talk. I'm going to talk about things on a larger scale. So I'm going to show a picture from the Hubble Ultra Deep Field. And it's the same one that Alex Filippenko showed you yesterday. The thing that's interesting about this is in this particular picture, if you have the whole picture, there are 4 stars. Here you can see, well, if I can move my finger, there's a star. You can tell it's a star because it has that little plus sign on it, right? Just like Alex, he's got an arrow to point to the supernova. We have this little plus sign. That's because the Hubble Space Telescope secondary is held up by 4 struts, and you're going to get 4 or 6 or 8-fold symmetry depending on the diffraction pattern you get. And so if you have a point source the way stars are, or close to a point source like stars are, they get a nice pattern like that. What that means is everything else in this picture is a galaxy. And then this little tiny grain of sand held at arm's length, there are more than 2,000 galaxies. And as Filippenko told you yesterday, that means in the visible universe, there are on the order of 100 billion galaxies. That is, in the universe that we can see, and we can guess that there are very many more galaxies than that. But in our visible universe, there are about 100 billion galaxies. And we got to explain why there are 100 billion galaxies. And it turns out by looking at this picture, you'll have to realize that the faraway galaxies, the little small ones, have different color and a different shape than the larger nearby ones. So there's an evolution of galaxies going on. We have to explain not only why there's so many galaxies, but how do they come into being and how do they evolve and how they're different. That's part of the task, right? You take on a big task. And so what I would say is that by the time you finished your physics courses in college, you should be able to predict that there should have been slightly more than 100 billion galaxies in this volume with a simple calculation. It's undergraduate physics. So the good thing is we're able to make progress about the early universe because it's actually simple, or at least it seems simple. And so that and one other feature, one other tool gives us hope in trying to understand the whole history of the universe. Okay, so here's the other feature, our primary CSI tool, that cosmic scene investigation. And it's basically looking out into space is also looking back in time, because light, even though it moves very fast, 300,000 kilometers per second, the universe is so big that the light travel time is extremely long. And so that we're able to use the time delay line of the distance of the universe to get snapshots of the universe at various epochs. So if we look at a sphere near us, we see things that are very recent to us in time. So the sphere that sort of just includes the moon is roughly 2 light seconds. Right? So you're only looking back 2 seconds. If you look out to the sun, it's only 8 minutes. Look to the nearest star, it's only 4 years. Well, if you had a picture of you 4 years ago, you're probably a little different now, but you could probably still recognize you. But go out to, say, the nearest 50 stars, and you're starting to talk 10 years. Go further, typical star, you're talking 1,000 to 100,000 years. Things are a little different. You go to the nearest galaxy, the nearest big galaxy, Andromeda. It takes light about 2 million years to get there. So if you took a picture of Minnesota with your giant telescope that was funded by a functional federal government, and you got a good picture of Minnesota, what would it look like, the picture you took today from if you're in Andromeda? Well, it would pretty much look geographically similar, but there would be no humans, no signs of humans. There'd be, there were, at that time, we think, no humans existing on the Earth. There were some animals and so forth, but there wasn't any evidence for man or more or some of the advanced species. So that's just the nearest galaxy, right? The nearest significant galaxy. You go out to sort of a typical galaxy, and you're starting to talk, hundreds of millions, billions of years. And if you look up here, now I got to find my arrow. You look up here, there's a thing called the Great Wall, and you will notice how far out it is, right, in terms of what it is. We're talking They're roughly 1 billion years. That takes light roughly 1 billion years. And you can see galaxies out somewhat further than that. You can see galaxies out on the scale of at least 6 billion years and maybe 10 billion years. But if you look back further to roughly the 14 billion years, you find the universe, which we know is expanding, was much smaller, and it was also much hotter. Its temperature we know now from the cosmic microwave background to be about 2.7 Kelvin. When it was 1,100 times smaller, it was close to 3,000 Kelvin. It was starting to be as hot as the surface of the sun, and you can't see into the sun because the ionized material stops you from going any further. And that's the situation we see, that when you get out to this outer surface, you don't see any further, right? Even though the beginning of time is just on the other side, right? If you could just see through that cloud, like seeing to the center of the sun, you would be able to see the very beginning of the universe, but you can't. The best you can do is look back to the surface, and I've spent a large part of my career making maps of the surface in some detail. But as a cosmologist, that's like find the initial conditions. If you understand the laws of physics and what the constituents of the universe are, you should be able to extrapolate forward and show the development of the universe. And if you take measurements in a series of concentric spheres, you'll have snapshots at different times, and you can compare the fingerprints for various models and various parameters with what you actually observe, and that's how you can see whether you really understand things or not, right? So you can test even things like, is the theory of gravity correct on large scales? You can compare various things to do that. So here's a recap. Well, here's almost a recap. So we live in a spiral galaxy. We don't live in the center of the spiral galaxy. We live in a spiral arm in our spiral galaxy. So in terms of verticalness, we're close to the center plane of the galaxy, but far out from the center. And so, well, find my arrow again. This is not a supernova. All right, well, I can't get it here. But we live out about in a place like that. We live out on the spiral arm. We look one way, we'll see the center of the galaxy and the plane of the galaxy. Looking the other way, we see the universe. Right? And around us are these modern galaxies. But if we look further out, so toward the edges, over on the left edge or the right edge, you see these irregular and different colored kind of galaxies that are out there. Go out a little further, you see that they have funny shapes and they have funny other kinds of behaviors. That's because they've more recently formed, they haven't come to equilibrium, and more often they have not merged together. Many smaller galaxies merge together to become the larger galaxies. So that's one of the reasons there are slightly fewer galaxies. The main reason is they spent a lot of time dissipating themselves and didn't quite make it to the big time. And then we have this period where there are no galaxies and there's nothing apparently going on. It's more subtle in there. It's the gases starting to form together before they make the first stars and the first galaxies. And then finally you have the cosmic microwave background, the embryo that shows the embryo universe, and at the outer sphere, that's the beginning of time. And the only thing wrong with this picture is there should be 100 billion galaxies in it, right? Get rid of the arrow. There should be 100 billion galaxies in it instead of just a few. So it's a simple picture, and it's not that we live in a special place, because if you were just to move over some other place, you'd make the similar sphere around it. And with 100 billion galaxies, you think statistically it should look very similar. It won't look exactly the same, but statistically it should look the same. So here's the kind of stuff that we're doing already. We have a very good map of the cosmic microwave background, because now we actually have the results from the third generation satellite. But we also are beginning to make maps of the galaxies. So you see, I can't move the pointer around very effectively. You see an outer sphere of galaxies that are relatively far away, but they're only partial maps of the sky, and you can see the spheres of those. And as you come in, eventually you see the Milky Way appear to be wrapped around us, and the Earth showing where we are. So this is an exploded view of the half spheres around us. There's another set of half spheres on the other side. So we're beginning to get a set of spheres. Each of these spheres at different distances are a different look-back time. Right? So you read off the bottom scale the distance in billions of light years, and that tells you how far it is. Unfortunately, it stretches and doesn't show too well. But so that is the kind of thing we're doing to understand the time history of the universe. And I'll show you pictures later on of how it should develop from a very simple, uncomplicated, relatively universe with very small variations to a universe which is extremely more structured and so forth. So let's go to the first surface. We've now had a series of cosmic microwave background missions. The cosmic microwave background is the relic radiation from the Big Bang. It's called a microwave background now because over the expansion of the universe, the wavelengths have been stretched to the point that from being in the visible when the universe was 1,000 times smaller, down into the infrared, into the farther infrared, and finally into the microwaves as what appears today. And when it was discovered in the microwaves. So the first mission was a mission on which I was one of the principal investigators and one of the team members. We launched in 1989. That's the Cosmic Background Explorer satellite. With that, we showed this radiation really was the relic radiation from the Big Bang, very definitely, very clearly, very precisely. But also we found indications for small variations in the amount there was. That is, we saw structure on the scale of a part in 100,000 variation. So it turns out the universe is extraordinarily smooth and uniform at the beginning. There's only just a little bit of blemishes on it that turned out to make the universe fairly interesting. The next satellite that came up was the microwave anisotropy probe, named after Dave Wilkinson, who died during the operation of that, and who was one of the pioneers in the field. And it was launched in 2000, and in 2002 started publishing its data, and actually COBE operated for 4 years. I couldn't convince my colleagues. The error bars went down linear with time instead of the square root of time. And they said, 4 years, how much more can you gain? But by the time we had WMAP, we learned, so it actually ran for 9 years. And so it was recently shut down. And it had much better angular resolution because we know we now are looking to exploit these variations and tell about the early universe. And I will show you in a little while. We know these are acoustic oscillations in the early universe. And just like striking a bell, the wavelength is set by the geometry of the bell, but the frequency of the bell set by the material it's made out of. By looking at these sound waves, you can tell what the universe is made out of, and you can also tell things about its geometry and so forth. So I won't go into details about that. I usually do. I'm going to spend my time on a little other stuff. And so WMAP ran for a long time, and then in May of 2009, we went to, some of us went to French Guiana, to Kourou, to see an Ariane 5 launch the Planck satellite, named after Max Planck. And it's I think the stealth version. It's the cool one. The first one was crude, and the next one was better, and then this one's the one that's the slick kind of setup. And it took a while because we went out to the Earth Sun Lagrange point, so we co-orbit with the Earth by the combined Sun-Earth gravity, and you're far enough away you can see many things. We've released half the data, and we're preparing to release the second half of the data from that mission. And that mission is actually at the point of turning down. But I have a nice little video to show you of Planck mapping the microwave sky in English and in Russian. And so this is the satellite. It has a very interesting configuration. There's a primary mirror, a secondary mirror, and a bunch of large number of receivers. And it has all kinds of things to make it operate very cool. And so some of the receivers work at 1/10 of a Kelvin, 1/10 of a degree of absolute zero. So here, the signal's coming in from the sky. Planck is not sending radar signals out. It's just selecting what data is coming from the sky. This is an actual Planck map as it's being mapped. You'll see the plane of the galaxies. It's at 62.5 degrees to the plane of the solar system. So at the end, we'll unfold this map and then rotate it around so the plane of the galaxy is across the plane. So you'll understand the configuration in which the maps are in. So you see the plane of the galaxy. This is what the galaxy looks like in the optical. Very different than what it looks like in the microwave. And if you remove your best estimated model, because we have many wavelengths, we can estimate what's signal from the galaxy and what's coming from the universe, you see the following map. Okay, so this map, doesn't look very impressive, does it? At least the other one was pink and blue, right? I mean, this one, it's a cosmic egg, but it looks very different. But in fact, if you study this, and if you've studied what we do is computer simulations of universe in various situations, you'll recognize there are features in here, and there are special features there are things that happen on big scales and things that happen on small scales, but there's one particular scale that gets picked out, and I'll talk about what that scale is. Let me show you one more picture that shows you what I think is the really cool spacecraft. You know, it's not just that it goes to 1/10 of a Kelvin and 20 Kelvin and, you know, and 80 Kelvin and so forth, and we're at 300 Kelvin in this room. It's a very complex thing. It's complex in a different way than AMS is complex. I mean, AMS is complex by having a large count and many different kinds of things. This is complex in terms of the overall system and how it works. And so if you look at the same patch of the sky as viewed by the same three satellites, this, you know, is picked to make COBE look bad and Planck look really good, right? And WMAP is in the same. But you see the same part of the sky where we were only seeing very large features with the Cosmic Background Explorer satellite because we had relatively small antennas. They got to be bigger radio dishes on WMAP with more resolution and even bigger and more sophisticated when we did Planck, so that we pick up, and we also use shorter wavelengths, so we pick up more resolution and we see the features more explicitly in the small scale, particularly because the noise is smaller and the resolution is better. So that's the sort of gain. So we've ended up with this model for the history of the universe that you saw flashed up here briefly. And it unfortunately was made a couple years ago, so it's 13.7 billion years. Now we're at 13.81, but you know, it'll change a little bit when we release more data. So what this model is there's a sphere around us which we can see. That is, light can have come to us over the history of the universe over 13.8 billion years, therefore 13.8 billion years plus a little expansion. And you take a cross-section through that and trace that visible universe backwards in time, going to the left, right? So on the far left is to the beginning of time. And what we see, the surprise that Alex Filippenko talked to you about yesterday, was for the last roughly 5 billion years, the universe has been accelerating. That's why it's concave out. The universe has been accelerating its expansion. Before that, for the 10 billion years before that, the universe was slowing down, and that's the period in which structure forms. That's when we get the complicated structures I'll show you later, when we get the stars, the galaxies, and eventually the solar systems. All of those had to form before the universe started accelerating, and only the things that were already in bound systems continue to form and reform and go on. Things that are larger than that are getting pulled apart by the fact that the universe is expanding and faster. And so it means what's going on. So if we look at the history, we see modern galaxies at the present time, and then as we sweep back to the left, we see galaxies that are younger and less evolved and younger and less involved until we get back to the universe was roughly 400 million years old, and that's when we believe the first stars started appearing and the first structure started showing up. And then we go through what we call the Dark Ages, when things were gathering. You know, the Dark Ages was a time where things were gathering. Well, first you went downhill, and then you gathered things together to have the Renaissance. Well, that's the kind of thing that goes on. But before that, at the 400,000 years or 380,000 years, we had the light from the Big Bang that illuminated the embryo universe. And then we had this period at the very beginning, which we think was a period of very rapid acceleration that took us from a situation where everything that's inside of the 13.8 billion light years in every direction was in a region much smaller than an atom, and quantum mechanics was a very dominant kind of feature. I think Lawrence Krauss, our great popularizer, is going to explain how we made everything from nothing, and we'll understand what a big role quantum mechanics plays. So what we're trying to do with our spheres is take these slices, remember take these slices and map them over time and see if this happened the way we thought it happened, and compare that to what we think are our best models of the universe. So part of the mapping is what happens later time. I talked to you about mapping and how much effort we've put in and how many years we put in mapping the very beginning, the initial conditions, which you should be able to propagate forward. One of the things about physics is if you know what everything is like at one time, you should be able to propagate everything forward and predict everything that's going to happen after that, at least on a statistical sense. But we have to see what's going on. So here's a picture that's got 1 million galaxies in it. This is, I will show you two different ones. This is the Sloan Digital Sky Survey. It's actually Sloan Digital Sky Survey number 2. And what you see are a series of dots, right? Each little dot on there is a galaxy, because now we're talking big time, and so galaxies don't show up so clearly. But every dot on here is a galaxy. And how do you get this? Well, you take a picture very much like the Hubble picture, usually with a big ground-based telescope. You take a picture, you got the angle, you then have to pick out what are the stars and throw them away, and the other things you are convinced are galaxies, you have to estimate what their radial distance is away from you. You make a plot, and you plot it out like this. And as so if you take one picture, you're seeing a cone out in the sky, and you see a certain distance until galaxies are so faint that your telescope is insufficiently large to detect the faint ones. And so it's not that there are not galaxies out here where this arrow is. There are still galaxies out there. They're just not bright enough to be seen with a 2-meter telescope, for example. And but as you take a series of pictures as the Earth rotates, that cone sweeps out a kind of a fan across the sky. And then you can't see some places because our own galaxy gets in the way. But you can also change to a different angle and get a different fan in the sky. So I'll show you the geometry in a kind of a movie. So you now see the fans from the Sloan Digital Sky Survey. And each of those white spots is a galaxy. And sometimes you see there are big voids where there are almost no galaxies. And other times there are many galaxies together. But there's another feature in here which will come swinging around because it's on this center one. So I can't get my arrow there. This thing here, that just went around. I should have stopped it. You see the arc there. That's called the Great Wall of Galaxies. It looks like a big string of galaxies. I pointed out to you it's like a billion light years away. So we're seeing there it is, what it looked like a billion years ago. But as you'll see, I'll show you another slice, and you'll see the Great Wall again. It's not just a string that happens to be in this one. It actually is a sort of a wall of galaxies. And so one of the questions we have is how many times should we see Great Walls of Galaxy? So this is the Sloan Digital Sky Survey 1 plus 2 together, but mostly dominated by Sloan 2. And there was a competing experiment which was run by another collaboration called the T-degree field of view. And we're going to, if the movie starts, we're going to fly through it. And you'll notice when you fly through, you see the galaxies. Of course, you wouldn't see them because we'd be going much faster than light. But anyway, you'll notice you see the galaxies, you see the shapes, you see the colors. This is a big data cube, right? Not only do we have things in 3 dimensions, but we have information about each of the things in there. So when we're mapping the universe, we're mapping it in more degrees of freedom. Now we're swinging out. We're going to look back and see the geometry of the survey, and it's just a consequence of surveys that they're going to have this kind of wedge shape because you're taking a series of pictures and you're at a certain altitude at certain location in the world. You're going to take a series of pictures, and as the Earth rotates, you'll scan out a wedge in the sky. And again, you will see there are these places where there are voids, and there are places where the voids are surrounded by skins, or places where the intersections produce a lot of galaxies. All right. So if there's no questions on that, I'll go on to what's going on now. Just, it's easy to find your way home because we're in the center in this picture. But anybody else made a picture, they'd put themselves at the center too. All right, come on, my computer. Okay, so this is Sloan Digital Sky Survey 3, known as BOSS. So BOSS is short for Baryon Acoustic Oscillations Sky Survey. And I'll explain what a baryon acoustic oscillation is in a minute. But first I want to show you what the BOSS Sky Survey looks like. So before, you see hidden in the center underneath the yellow and the red, that's the Sloan 2. So BOSS is we're trying to measure 1 million galaxies per year. So it's a little harder. You have to do 1,000 galaxies at a time to do that. And so that's a non-trivial problem. And we do it mechanically now. And we're trying, in the next generation, we're going to try and do it with little robots. So it's a thing like that. But you'll notice there's something funny. The galaxies are not uniform in the sky. It looks very full. It's very white in the middle, right? That's because you can see every your telescope's big enough to see every galaxy. But as you get further out, they're too faint. But then you start seeing there's another set of galaxies. And then far, far away, we're seeing a whole lot of stuff. How is that possible? Right? Well, it's because there's so many galaxies, 100 billion, and so little time, you have to choose, right? And what you do is you choose some. So here's what the survey really looks like. right? You don't look so many of the close ones. Well, first, there are not so many close ones, but you particularly try and find things that are out at a distance which is corresponding to roughly a redshift of 1, or about 1,000 megaparsecs, which is roughly 3,000 million light years, which is, or 3 billion light years. So it's a big fraction of the sample size of the universe. You try and pick galaxies that you think are roughly at that distance before you really make a careful measurement of them and really estimate their distance more carefully. That's in order to sample this kind of test, because we're looking for things that are going to be a test of the dark energy and of the dark matter. And so you think if that's your hypothesis, there are certain places you should look in the history of the universe that will give you information about the changeover and the variation of that. But the other thing that's kind of funny is if you look out past the red lines, you will see that each red line terminates in a blue dot. The blue dot is a quasar, and the red lines represent what we call the Lyman-alpha forest. So the Lyman-alpha is one of the lines of hydrogen, and so if you have an ultraviolet source and you run across a hydrogen cloud, it will absorb. And if the hydrogen was uniform, you would get kind of a trough, but if it's starting to bunch up in clouds, you'll get dips each place. And there's so many dips, it looks like a forest, right? You just see line after line. I should have a plot on here, but I don't. So the reason you have that kind of an interesting looking survey is because you actually deliberately target certain kinds of things. So you have many fewer quasars, but from each quasar you get many points because you get many absorption lines along the way, and you try and study what the universe looked like, at 3,000 megaparsecs and at 1,000 megaparsecs. You're trying to see differences in what was going on in the world. And right now, this is what I spend more of my time on than BOSS. I spent a lot of the last 2 weeks worried about fiber testing. So we're going to try and measure on the order of 20 to 50 million galaxies. So you have to stay on Moore's law. If you're ever going to get to 100 billion galaxies, you got to double the number of galaxies you measure every 5 years, or you're never going to get there. And so we want to measure 5,000 galaxies at a time. And so what we want to do is have 5,000 fibers. Each one, a little robot, puts right on the image of the galaxy. So it's a wide field of galaxies. You put every place where there's a galaxy is interesting, you have a little robot, put the fiber there, and then you run the fiber down off the telescope into a spectrograph room where you have 10 times 3 spectrographs, and you run, each one of them does 500 galaxies at a time. That's how you do the experiment. But the problem is, if you're going to be tracking with the telescope, there's an alto-azimuth, there's a rotation and a twist that goes on. And so we built a little machine to rotate and twist fibers, and we're testing to see how the light from the galaxy, because you can't waste any light from a galaxy because they're relatively dim, and it takes more time to observe if you waste any light. So that's what your life is really like when you're doing these massive things. What you're really doing is worrying, if I move this fiber around, will anything happen? That's the reality of it. And so the goal there is to be measuring 20 to 50 million galaxies and on the scale of 1 million quasars in order to really get statistics. And then if we get to 50 million, 50 million is a lot, and it's a big job, but still 100 billion is a long way to go. Okay, so now we're coming to the dense part of my talk. Okay, and I'm going to try and teach you something, and that is why we have dark matter, right? We always hear dark matter the historical way. Well, we need it to hold the galaxy together, hold the clusters together. That's not the truth, okay? Here you go. Here's the evolution of a single overdense lump in the universe. You'll notice this is done in such a way. You took a nice smooth density thing, for those people who are experts, a Gaussian, and you let the Gaussian go at the beginning of the universe, and what happens is it separates into 2 pieces, a spherical outgoing shell and the original dense lump, right? Slightly reduced. Okay, so this reminds me of an old story that roughly 100 years ago, this old uneducated man came out of the wilds, and he came into town and saw this guy eating his lunch, and he said, "What's that thing you're drinking your liquid out of?" And he says, "The thermos." He says, "What's the thermos?" He says, "Well, it keeps hot things hot and cold things cold." He says, "How do it know?" Right? So how do it know to split into 2 pieces? Right? What tells the matter to do this? Right? I mean, because every point should be like that. So this is a single one. You have to imagine the universe is filled with a huge number of fluctuations like this, all doing their things at different times, some oscillating, some doing that, but all of them having this spherical shell going on. So we're going to go from this two-dimensional situation. So it's a sphere, a spherical shape. I've made a slice. You see part of the sphere going out, and you see on the third axis, you need to show the density, right? So I'll show it to you just one more time, just because it's fun, right? It's not like it was a fluid, and it dropped in and the wave went out. This is really more than that. So we're going to go to one dimension, because it's spherical. We're assuming symmetry. Go to one dimension, and we're going to realize the universe is made out of constituents. It's made out of dark matter. We're going to start when the universe is 110 years old. So by then, the quarks and everything are all gone, and we're into protons and neutrons, and they've turned into the light elements. So we call that gas, or baryons, for baryon acoustic oscillations. We have the light, the cosmic background radiation. There's photons. And we have neutrinos. We also have gravity waves, but they're not interesting because they just go their own way because they interact so weakly. Okay, so we're going to start out with this, and they all lump up the same way. And that's because in the early universe, you put a perturbation in, no matter what you do, there's so many interactions going on, it re-equilibrates, and it becomes to every degree of freedom is equally populated. So no matter what you do at the very beginning, you get this nice kind of a distribution. It's only a question of its shape. Now, this is the tricky part. I'm going to start it off, and we'll see what happens as time goes on. Okay, let me stop it for a second if I can. So you'll notice the dark matter pretty much stayed in place, but it actually expanded a little bit. And this is because this is cold dark matter, but it's not completely cold. There's small thermal velocities, and the universe is expanding, but this isn't co-moving, so it stays fixed on the scale 6 on. So the black stuff stays there as a lump, and it hardly changes. But the red and the blue, that is the gas, the baryons, the electrons, plus the photons, plus the nuclei, are really, really tightly coupled. They act like a single element. And that's because light and electrons interact extremely strongly, and electrons interact with protons extremely strongly. They all get bound together very tight, and they act as a single fluid. And you see how tightly they're bound. And the neutrinos, unlike the gravity waves, actually interact enough that they're lagged behind. They don't just disappear. They leak out faster, but some of them are still trapped. Okay, now the question is, can I make it go a little further without no, I got to start over. Okay, so now we're going to follow it out, and it keeps going like that, till you get to the 400,000 years, and now you'll notice something has happened. At 400,000 years, atoms start forming, because the universe has cooled down to 3,000 degrees, and so you can start forming neutral atoms, and the interaction between the electrons and the photons is pretty much cut down by many orders of magnitude. And the electrons being bound into the atoms, the photons begin to free stream, pretty much like the neutrinos are starting to do, and the gravity waves have already done, and they start separating out. And so the light's going to come to us and show us this spherical shell directly. Just like if there was a big explosion on the sun, the surface of the sun, we'll see that explosion, and we'll see those kind of things. So it's roughly 400,000 years that this happened when the universe was 1,000 times smaller. I didn't stop it quite soon enough. But you'll notice something funny happening near zero radius. You'll notice the baryons are beginning to be pulled back in and come back onto the dark matter. Okay? So the dark matter is not necessary to hold the structure together. The dark matter is what is the structure. It starts and forms the structure. The baryons just happen to fall into it like dirt falls to the bottom of your bathtub. It's the true structure in the universe. All right, let me see if I can go further, and you'll see what happens. All right, well, my fingers aren't sensitive enough here. See if I can stop it at the right time. All right, see, at this point, what you're seeing is that the neutrinos are free streaming out, the photons are free streaming out, and the baryons are falling back into the potential well of the dark matter. But out here, at 150 megaparsecs, or roughly 450 million light years, there's an extra amount of baryons left around. There's a spherical shell of baryons that are left behind. And those baryons, in the end, if I can make it work, or I have to go around again, are going to pull up a little dark matter. Well, you saw a hint of it. We'll see if I can get it. If you watch to the very end, you will see at that little bump, instead of the dark matter pulling the baryons in, the baryons pull a little dark matter into that little bump. So right there, it's starting to happen. And at the end, you get slightly de-enriched dark matter compared to baryons in the center. But they trace each other almost perfectly, right, in a certain kind of sense. So this is why the spherical shell goes out. It's the photons pushing the electrons and the baryons out. And then when the photons release them, then everything comes back and falls into the potential wells that is left behind. But there's a small residual left behind, which is quite large. It's on the scale. We see it both in the cosmic microwave background, but we see it in the residuals of the galaxies. In the cosmic microwave background, it's a very big feature. In the galaxies, it's a relatively small feature. So if you do it in terms of angular scale, so roughly the 1 degree angular scale, so angular frequency on the bottom axis or angular scale on the top axis, and compare that to galaxies you see, around the large cluster of galaxies, you see an extra spherical shell of a few percent extra galaxies. So a huge cluster of galaxies will have a few percent extra galaxies. And that's the baryon acoustic oscillations. So this is now our second tool for studying the dark energy, the acceleration of the universe. The first tool was a supernova, which we call a standard candle. That is, as Alex and Lopinko tell you, they were standard brightness. And then the second kind is the baryon acoustic oscillation. They're a standard ruler. There's something whose size we know, because it's very easy to calculate the speed of that sound going out. Turns out to be, in the early days, the speed of light divided by the square root of the number of dimensions, which happens to be 3. And so you get a very well-defined things. And only at the very end do the baryons become important and slow it down a little bit. But that's the kind of things you see. Then there are two other things that are just becoming interesting: weak gravitational lensing and cluster counts as other ways of understanding both the dark energy and the dark matter. And so we're looking at a small regular size, the most common kind of spot size, if you go right into angular space instead of angular frequency space, a spot size being a sphere around a cluster size out in the survey. But it's big. It's 400 million light years, so you got to do really big surveys. So the idea here is we're going to measure the universe. We need tools. One is the standard candle. So this is supposed to represent the brightness of the candle dropping off at the square of the distance in Euclidean space, and a standard ruler, the angular size dropping as 1 over the distance, right? And so it's a standard ruler, again, emphasized. And here were the first set of results that I showed you in 2005, where you begin to constrain what was going on. You can compare omega matter to omega dark energy, labeled as omega lambda on this axis. And the CMB was telling you one wedge. Supernova were telling you the other. Clusters were giving you just the matter, but the baryon acoustic oscillations started telling you another thing. And there's a concordance area, and that's the area which is around 70% of the energy density in the universe being in what's causing the acceleration. And you can even try and find the equation of state, and you find it's very close to what you would expect for the cosmological constant. So this is where we were in 2005. This is where we are now. We can measure the look-back time by measuring the distance and dividing by the speed of light, and compare that to the size of the universe, which we measure the redshift. So 1 plus the redshift is the ratio of the size of the universe when the light was emitted when the light's received to when the light's emitted. And so you see this line on there, which is the prediction of a lambda CDM universe, and you see the data from the supernova, and you see the data from the galaxy mapping, from the baryon acoustic oscillation mapping. And you see the comparison, and you see they're very consistent. And so one of the things the CMB is so powerful, it really sets the model of cosmology, many of the other parameters, and that means the new measurements that come in can then focus in on testing one thing. So this is the state of the art we are today, And the only thing that's different from the Euclidean picture that I showed you is the universe is expanding. And so if you have something that's a fixed size and the universe is expanding, there's an extra 1 plus z factor that goes in there. So you would think in Euclidean space, the luminosity distance, brightness falling off is 1 over the distance squared, and the angular diameters would be the same, and they are. But when you have an expanding universe, even if it's a Euclidean universe, then you have this extra factor of ratio of sizes. And for those who really care about the details of what's going on, here's another one of the same picture of the distance versus the redshift. Usually, if you're going to think of the dynamics, what you're really doing is saying, here's the present time, and I'm looking to see the universe is accelerating and then slowing down and accelerating. And so the supernova, the more distant supernova and the Lyman-alpha get out to the part where the universe was still decelerating, but the nearby stuff is when the universe is still accelerating. Now, for a couple of the experts that are here, I have this one slide to show you the most recent results, where there's a little bit of tension between the various measurements, but they're all sort of still in the same neighborhood. They're still around that the dark energy content is on the scale just below 70% of the energy of the universe, whereas the matter is just around 27% of the energy density in the universe. And, but you can also do tests to see what the equation of state might look like and what the change in rate of the equation of state. And with the measurements we have today, we have the best measurement of the equation of state at roughly a redshift of 1/2. That's when the universe is 1.5 times smaller. And then we have a limit, only a sloppy limit on how much it might be changing on either side of that, because that's where we have our measurements as of now. And so there are various parameters, but I just put this up for the few experts. Now this is a picture of the evolution of the dark matter alone. It's a simulation by Andrew Krasoff. I think Alex Filippenko put it up briefly, but we'll watch it again from the beginning, not the real beginning, but when the universe was roughly 10 times smaller. And you'll see it's pretty uniform even when the universe was only 10 times smaller, because it was extremely uniform when the universe was a lot smaller. And then you first get little peaks of things forming, and then the peaks link together into a network, a sort of a cosmic web of dark matter. You see the shape and so forth. And that's our idea of how the structure in the universe is existing. It's driven by the fact that the dark matter is at least 80% of the energy density in the matter, and it provides the structure upon which the Christmas ornaments we see, it's like a Christmas tree, and then the galaxies are lights, like Christmas lights and so forth. So I'll show you the concept of the next simulation. This is the distribution of matter versus scale. So we're going to look on the large scale, and then we're going to zoom in on the small scale. And we're going to keep the dark matter looking white, even though it doesn't interact so directly with light. So light would go through it. It should be invisible, but to see it. And the ordinary matter, we're going to have yellow like the sun, because it can fall into the potential wells and eventually radiate away some energy so it can collapse and form stars and galaxies. And so here's the Millennium simulation with 10 billion particles. And we're starting out where the distance is 3 billion light years across there. And it looks pretty uniform on the average, but there's a huge amount of structure when you look on the small scale. You see all these filaments and all these voids around the filaments. And where many filaments come together, you get a large cluster of galaxies. A few filaments come together, you get a small cluster of galaxies. So for the zoom in, you zoom in on a place where the most filaments come together. It's like zooming in on the Great Wall. It's, you look for the most interesting and unusual object. But if we lived not in a small little cluster of galaxies like we do, we live in a village, it's like St. Peter's. We don't live in downtown Milwaukee. This would be downtown Milwaukee or New York or Chicago or something, or Calcutta. Right? But as you zoom in, you start realizing if we lived here, no matter which way we looked in the sky, we would see galaxies. Whereas you have to go to a lot of trouble and be in the right place to see Andromeda, right? You can see it out of the corner of your eye on a really clear night. So this is zooming back out. And then Alex showed you a little bit of the fly-through. So this is the fly-through. And remember, the white is the dark matter, and inside in the yellow is the ordinary matter. And what you realize, the ordinary matter falls in and becomes like the dark matter, but then it can dissipate more energy, and then it falls to the bottom. Just like, when you take a bath, the dirt goes to the bottom of your tub, falls to the bottom of the potential well. The cooler particles are able to fall in more. So that's the reason we want dark matter to be cool, so that it actually clumps, or relatively cool. It can be warm to cold, but cold is easy to calculate. But then the ordinary matter starts out warm, but it can radiate away and come out more. So our concept is, our concept is we can go from the anisotropies in the cosmic microwave background, run a computer simulation where the only thing that we really worry about is gravity, and we just let gravity work for its 13 billion years, and we end up with this complicated network that's highly structured, and in these intersections and along these filaments is where we see our galaxies. Okay, so here's a sort of a pi wedge simulation starting, over on the left side of the here and the now, near where the arrow is. And as we look back in time, or we go to the beginning of time, the universe is very hot and very uniform. And as it cools down and the radiation releases the material, structure starts to form, and gravity works and makes it more and more nonlinear and more structured, more and more of that the kind of void and filament shape that goes on. So just so you can see the texture again, there is without all the writing on top of it. You can see we start out with an extremely uniform universe that is on average, so 1 part in 100,000 variations, to where we have huge variations at the present day and much more complicated kinds of structures. And that's an interesting kind of thing because it tells us something about how the universe was created. Okay, so here are the pictures with a nice label, the era of grand discovery unfolds. So on the upper left is a picture from the 4 years of the COBE DMR, and it's with the best estimate of the galaxy removed and smooth, so the signal to noise is reasonably good. And you see a number of large-scale structures which are very significant. And down below is an image of the Earth smoothed to the same resolution. And you can say, well, those two maps, they do look a little different, but I can't really tell the difference so much. I mean, all the continents are in the bottom. Maybe all the continents in the universe are in the top, but they don't look so different. Who knows? There's not enough statistics there to really tell. But on the right is the I haven't updated it to the new Planck results. It's the WMAP, I think 5 or 7 year data, and the bottom is the Earth with the same resolution as Planck has now. And you'll notice there's no way you're going to confuse the top and the bottom, right? And why is that? Well, it's very obvious. You look down the middle of the Atlantic and there's this mid-Atlantic ridge. It's this long, sharp feature. It's a long, thin-edged feature. And the only way you can have features like that is if you have nonlinearities, that the forces that shape the surface of the Earth have to have nonlinearities in them for the phases of all the long-scale structures to line up and have sharp edges like that. So you get continental edges, you get these continental drifts and so forth. That the forces that shape the Earth are tremendously more complicated and more difficult to deal with than the forces that shape space and time. You look on the upper map, you don't see long, sharp edges. You just see kind of random noise. And all the different ones appear to be relatively independent of each other. And when you do a careful statistical analysis, you know that they are actually independent of each other to 10 to the minus 4 level out of their 10 to the minus 5. So linear perturbation theory works incredibly well in this situation, but it's telling you whatever was inflation or whatever created space and time itself was an extremely linear process. It's extremely linear for us, and it's extremely simple that it doesn't produce non-Gaussianities and nonlinearities in any simple form. My talk might be over early. All right, well, it's getting close to the end anyway. So now I'm going to show you movies. Okay, that's all the science for you. Now it's pretty pictures from now on. You can relax. Okay, so maybe. Apparently my disk doesn't like being full. All right, let's see if I can restart it. Otherwise, we'll go to the final movie. Okay, so we're going to fly out from the universe, from the solar system. So that thing in the middle is the sun. And my friends and I are not the only ones making maps. It turns out that a number of astronomers, and particularly the mission Gaia, have been mapping the stars, and they've mapped approaching 1 billion stars. And so this is flying through those stars with the relative brightness and their locations known fairly well. And so it's pretty impressive to think that you might have a good fraction of 1 billion stars that you've mapped the location of. But you'll realize that there are probably 400 billion stars in the Milky Way, so you haven't even got to 1% yet. So you have to go to French Impressionism to try and make an idea of what the galaxy really looks like, right? So that's why in the other picture, I had to use a picture from another galaxy, right? But here are our nearby friends, and get to know them well, because if the accelerating universe, the dark energy, keeps working its magic, all of these guys are going to merge into one galaxy, and everybody else is going to go out of the horizon. So there'll be only one galaxy left. So they're all our friends. And because you got to go a long way till you get to the next galaxy. And the next galaxies that you see are actually pretty small. There's one little one out there and another little one. You have to go a long way till you start getting to groups of other galaxies. Of course, you also have to go in a direction that you've looked, right? So you know where the galaxies are. My computer really believes it's full. And eventually you get out to where you can't see regular galaxies. You can see the large red luminous galaxies and the quasars, which are shown in red. And that shows you the fan-shaped kind of a survey that you do, where you've got everything close by, but only a few of the brightest things far away. So I have another continuation of that. So here's the survey I showed you before, but now going out one of the fans to where you get to the large red luminous galaxies and then the quasars. And then outside of that is the cosmic microwave background. And the cool thing here with an animation is that it lets you go outside the observable universe, but it doesn't show you what's out there. It just lets you go out there. So we have this far mapped. Now we have almost double as much data as this, but we have partial movies, but we haven't made a full movie out of it. But this is sort of how the thing looks in terms of what we've done in thinking about mapping the spheres around us in order to map the history of the universe and test our models of the universe to see if we really have it right. So we have this fantastic universe, artist's conception anyway, where there's some amazing thing going on at the creation, and either creation from nothing or creation from a big mess, and then all these wonderful things happening, and finally modern galaxies and other things going on, or this old-fashioned picture that I showed you before. So now I want to show you all this, instead of showing you the latest Planck data, because it's, whatever the kind of test, I'd like to show you a movie which is based on all actual data. So I have a movie that I was going to show you before, which was made, as a commercial movie that in 1997 of a trip very similar to this, but a lot of stuff had to be made up. But now we don't have to make up so much. Okay, so we're starting from the highest point in the Earth in Tibet. The highest to the lowest point in the Earth is 28 kilometers. The radius of the Earth is 6,000 kilometers, so that's roughly a part in a couple of hundred. The universe is a part in 100,000. So the universe is way rounder than the Earth is. But when we get far away, instead of all these interesting features like the Tibetan Plateau or the big lava flows in India and so forth, you just begin to see how round the Earth is. Okay, so now you see the artificial satellites. People have been busy. There's a white line here just below the arrow. I was trying to put it on the arrow, but it shifted around. That's a geosynchronous belt. So we actually have a ring around the Earth. As close as they can be put together, there are satellites all around the Earth in this ring. It's called a Clark belt. But it's the geosynchronous orbit belt where the geosynchronous satellites are that are broadcasting communications and entertainment down to the ground. Also commercials and educational programs. Further out, you see the moon's orbit. There we're at a light second. And you see the inner planets. we get towards the outer planets. Already we're an hour, a light hour away from the Earth. And then a day. And you see the zodiacal constellations, and you'll see some of them are real groupings of stars, some are fake, because as you go past them, they'll distort, right, very severely. Some are just accidental alignments on the sky. They're asterisms. See them distort as you go far away. This is as far as humanity's radio signals have gone. And again, we're in the business of French Impressionism. So we're 100,000 years away. Now you're seeing our neighborhood galaxies. And the galaxies have been mapped so far. And some of them are color-coded because they happen to be in groups that have been studied, and people have particular fondness of them. There's a whole places where we haven't mapped, where our own galaxy makes it more difficult to map. And if you're going to spend your time mapping, you should do it where it's easy to do. And then the red luminous galaxies and the quasars, and the cosmic microwave background. So it's the same pictures I showed you before, just done with reasonable production value. And it's already time to make a new version of this, but it takes a while to gather resources to do that. Now I'm going to take you home, because my talk will be over, but I shouldn't leave you at the edge of the universe. Okay, so which one is our galaxy? Find your way home without the map. Well, there it is, clearly. You recognize it anywhere. Now find the sun. There's no place like home, right? I think that's enough. I'll stop at that point. So we have a little bit of time left for discussion.
Thank you, Professor Smoot, for that illuminating lecture and for bringing us back home. At this point, I'd like to call our panelists up for our question and answer period. And I'll remind folks that you can submit questions either on the internet using Google Moderator or by writing them on a piece of paper that the ushers have and sending them up to the front. Thanks. Folks, at this time, if you could find your seats, please, we'll get started in just a minute here.
A question already? All right, we'll begin, as always, with questions from the panel, and Professor Krauss has a question.
Thanks, George, especially for the inspiring movie at the end, which I was really remarkable. You touched on it a little bit, but I thought maybe you might want to talk about the future of what's next, and what are the major breakthroughs that might, we've had this incredible golden era, and so I thought maybe if you wanted to talk about the future.
Well, the part of the talk that I talked about was the fact that we're doing BOSS now, or Sloan III, and we're doing BigBOSS, and presumably there'll be a new generation of people who will be cleverer than thinking of simple little robots to move cables around, because doing 5,000 of those is a big deal. But we also have, of course, proposals for satellites, WFIRST and Euclid, and I think it's fairly likely we'll soon find out that Euclid will go forward. Euclid is, usually they don't name the satellites until after they've been through study and so on, but it's named after Euclid for Euclidean geometry. But the goal for Euclid is to be measuring more about the dark energy and about the equation of state, or whatever the properties are. And I didn't have time in my talk to do, but one of the things that you can do besides measuring the trajectory, the kinematics, how the position is changing with time, and that eventually tells you the dynamics. You can also measure what we call the curve of growth, how structure forms. And that is slightly different depending upon whether the dark matter has different properties or whether gravity is different. So it's a way to test whether general relativity has got some little moderation by doing a combination of those. And that's why I was saying you really want to have 4 ways of measuring the things about dark energy, because if you measure with more ways, you have more cross-checks, but you also have the ability to test whether the actual laws of physics you're using are correct by intercomparing and see if they give the same parameters.
Okay, I also was thinking, what's the next new window? I mean, the CMB, I have my own thoughts on it, and then there's this mapping of hydrogen lines, and what do you think what's your opinion of the next big new window on the universe?
Right, well, I believe that the next really interesting window, I hope, will be the laser interferometer in space. That is the measurements of gravity waves.
Yeah.
And I think that LIGO, which is operating on the ground, is looking for things like spiraling neutron stars, and which must happen and do that. But if you can make a much bigger interferometer that looks for longer wavelengths, you will see lots of interesting things happening, because in the center of every galaxy, as far as we can tell, there are black holes, and they're going to produce a large number of gravity waves that are measurable. Your problem is going to be actually to separate the different. There's going to be so many signals to separate them all. You'll be confusion limited if you're not careful. And so I believe that is a new kind of a frontier. Being able to probe into the beginning of the universe with gravity waves, that's a much further dream. But you have to start somewhere. And all of us are impatient. We would like to go and test string theory right now, but we're going to have to do it in steps. We're going to have to learn how to do these. I mean, when I look back, it's always embarrassing. I spent 30 years learning how to make these CMB maps. But you had to build the technology, and you had to learn how first to make the receivers and how to do the measurements. And now we're talking about measurements, which the pictures that presumably you will show, where we're making measurements in the microkelvin, so a part in a million. But in order to measure the really sophisticated kinds of polarization, which I didn't talk about, you're going to have to go to nanokelvin. And that's incredibly difficult to do from a great distance. And yet, I think it's within reach.
I actually have a question to ask you. You showed COBE, and then WMAP, and then Planck. There's this James Webb, which one reads on the newspapers. What is the major advance with that?
So the James Webb is a bigger telescope than Hubble, but it needs to be because it's working at longer wavelengths. But it's designed to go into the infrared in order to look back to greater redshifts, because if you think about when the universe is 30 times smaller, the light stretched 30 times coming here. So things that were in the visible or in the blue are then shifted into the red and the near infrared. So if you want to see that first generation of stars and galaxies, you need a telescope that's able to probe into that kind of stuff. So it's designed to look in what I would call the intermediate region, so sort of the redshift of a few further down and study those and so forth. Now, Alex may have his own view on these things. I don't remember spectroscopy on the telescope.
Well, the James Webb being tuned to the infrared, we hope we'll see the very first generation of stars and galaxies. I mean, we're almost there already, but with the Webb, we hope to get there.
Right. So I have another talk that I don't give, which is a talk about using gamma ray bursts as a way to measure the star formation history.
Well, in fact, already the highest redshift discrete objects known are the gamma ray bursts. It's no longer galaxies or quasars. And there's gamma ray bursts known at redshift 9 and 1 that looks like it's at redshift 10.
And it's not...
You'll be in the Lagrangian point. You can put into the Lagrangian point, right, James Webb.
Yeah, that's where it will be located. That's right. So it will not be in low Earth orbit like HST. And so that has the advantage that the Earth won't take up half the sky. It has the disadvantage that we're not going to be able to visit it and fix things if things go wrong. And we know that with the Hubble Space Telescope, something went drastically wrong, initially.
But it's worth pointing out that when there's a reason to look at the first generation stars. It's not just that we want to do maps and get pretty pictures. It's that there are some real controversies and questions about, because quasars happen so early, what formed first, stars, black holes, and that's going to tell us about structure. So that in principle is, I think, if you wanted to ask for the physics mission, is to try and assess why stars formed when they did, and what were the first objects that formed, and how did that feedback happen between stars and galaxies.
Right.
I looked into the design a little bit. It's a really beautiful instrument.
Beautiful if it works. But the whole mirror has to unfold in this way like a flower.
And see the sun. You have to
and again, if anything goes wrong, it will not be fixable. That's a real concern.
And we hope it'll get up. I mean, all of us who are particle physics and have experience, it's almost, as you probably know, the James Webb's almost been killed at least 2 times.
Yeah.
And every year that it takes to delay it because the funding is decreased, it costs more. So there's a reason for our people who are anti-James Webb to say don't build it, because every year you delay it, you've got all the cost of all the engineers and other people. And so one hopes that it'll actually fly.
Yeah, because it's really incredible to be able to put such an instrument there.
Professor Shears has a question.
Yeah, it's a slightly different question, and it's all to do with what our respective fields might learn from each other. So coming back to this question of dark matter, you showed simulations of dark matter in your talk that were based on gravity and a model of how it might form, and then based on how well it matches up to what we see today. Now, we heard yesterday that we could look for dark matter directly, warm dark matter, cold dark matter, and I wondered how sensitive your models were to any input that we could give you experimentally, how much difference it made, and if that information's already going into your investigations.
Right. So the reason I put that in was to point out that it's not that dark matter is just there because we needed to hold galaxies together. We don't get formation of structure if we don't have the dark matter. And I dwell on that little part saying this is cold dark matter, but even the little bit of temperature it has and the expansion of space caused it to have that extra term that went out, which is what gives the stuff for the extra baryons that were sitting out there to be able to pull some in, even though most of them were collapsing back down. So it depends on which situation you're talking about, whether you have things to learn about, because if you look, the dissipation, the dark matter can't dissipate energy so much, so it forms in smaller things and they agglomerate together to make galaxies. And the question, there are many things that come up. So the question of when the first objects formed and how massive they were when they formed. How do you get the very first stars? It's hard because they don't have the heavy elements in them to assist in the cooling. So that first generation of stars is a very tricky issue that's to do with. And you want more massive objects in order to form them and so forth. And so it turns out you get lots of there's many places things cross. So Alex mentioned there's this possible gamma ray burst at a redshift of 10, right? So it turns out that's getting to the point where it starts to cut into allowable warm dark matter. So right now, even though most people favor and think about and do their calculations with cold dark matter, you haven't actually ruled out warm dark matter that's below a few keV, so higher mass is equivalent, or your Bose-Einstein condensates have to be that way. So it's surprising because you think they would be ruled out, but they haven't been ruled out. But in order to form a massive enough star to make a gamma ray burst at a redshift of 10, you can't have a lot of the dark matter be warm dark matter. It has to be cold in order to have done that, but it also has to be cold and to make massive enough thing to make some of the metals we're seeing. So one of the other big advances is that the gamma ray bursts are so bright that you can look at their light and see absorption lines and see that some of the places have already formed a lot of the heavier elements quite early in the universe, much earlier than you would have thought. Right?
Let me just take a second to clarify for the audience, because this is a bit jargonish. Cold dark matter is dark matter that's moving around very slowly. It's like cold objects don't have much molecular motion within them. Warm dark matter has particles moving around more quickly, and hot dark matter is dark matter where the particles are moving around at speeds that are a significant fraction of the speed of light. In fact, neutrinos, for example, are traveling nearly at the speed of light. That is a form of hot dark matter, and that's been largely ruled out as a major component of dark matter.
And the reason is because cold things collapse and hot things don't. So if the hotter it gets, the less structure you're going to have on small scales because things move away. So that's the connection between the hotness and having the structures that George was talking about.
It's just that we use these terms because we grew up with them, and they're not exactly entirely intuitive.
Right.
Yeah.
So I think we should even step back one further step, which is you may wonder, with all these observations of dark matter and what it does, why we are so ignorant about, we say we're ignorant about what it is. And the basic reason is that gravity is sensitive only to the total mass basically within an area or volume. So it doesn't matter what the mass is made out of. It could be made out of heavy particles that weigh much more than a proton, or it could be made out of very, very light particles. It doesn't matter. It's just the total accumulated mass that we're sensitive to in these gravitational effects. So when we say we want to determine what the dark matter is, we want to see it in some other way than through its gravitational effects. We want to see how it interacts with other matter, how it might absorb light very weakly, for instance, or how it might come together and annihilate emitting cosmic rays. So that's sort of the framework in which this dark matter problem is posed.
I wanted to ask a different question. I come from the wild west of physics, namely theorists. And of course there are things like cosmic strings that some of us have thought about. Can you talk about a little bit the potential for ruling out some of these wild west ideas?
All right. Well, fortunately I have done some studies looking for cosmic strings and have not found them. Because if I had, you'd heard about it, right? But there are many ways you could see it. So cosmic strings are very interesting because there are possible ways of going from an earlier configuration of space-time, in what we used to call the vacuum, but it's space-time, where it's more energetic, and then you go through a phase transition and it becomes less energetic, or you have things left behind. And there are various ways that it can happen. There's one-dimensional ones where things become like hedgehogs and everything's coming out, or zero-dimensional, and then one-dimensional are strings. They have a mass per unit length, or they could look like a string. There could be extra dimensions. You can have extra dimensions that are small, and then have this compact energy along that. And so they show up because they have very interesting metric features. They don't make space non-flat. Normally you put mass energy into the universe and it makes it bends warp space-time. But a long, thin string, what it does is makes pi different. It takes a defect angle, which is equal to the mass per unit length in relativistic units, out of it. So we've been able, by looking, if you have a string and it's not pi around, light from my eye can get to you around both sides if you happen to be along the line of my finger. So you would see double images of things. So we've done searches through like the cosmos field, and so the Hubble has these wide fields that it's did, looking for pairs of galaxies that look identical, and then seeing if it's just accidental or there's a little bump on there for strings or whatever it is. But you also can see it in the cosmic microwave background because the strings have tension in them and they try and straighten out and they have a sideways velocity, and that creates a boost. So you have a temperature step across the string, and you can look for that. And I've done searches both ways, as have many other people. And all we've been able to do is set limits, but we're setting limits where the mass per unit length is around 10 to the minus 6, 10 to the minus 7, depending on how confident you want to be. And but now even string theorists are saying, well, if we have all these extra dimensions, we could have strings whose tension was relaxed to the point that they could be either one-dimensional or multi-dimensional strings that look like a linear defect, and you could observe them. But then they could look like a zipper, because if you have more dimensions, you can make two come together in a Y joint, and they can move around. So you could distinguish them in principle, but in practice, we've never found anything. So,
let me just, when we talk about strings and dark matter, Frank Smart reminded me that it may sound to the audience like we just sort of invent all these things we can't see, and the point is it's quite natural that lots of stuff exists that is difficult to find, and in fact it's when you think about it, George's work over most of his career has been the cosmic microwave background radiation. There are a billion particles of light in the universe for every proton. So it's a billion times more dominant in terms of the amount of particles out there. But it wasn't discovered until 1965 by accident. And so even the most visible thing in the world, which is light, was invisible until 1965. And so it'd be very surprising if there wasn't more out there that we couldn't see. It's not as if it's a great stretch of the imagination.
Okay, I've got a question for Professor Smoot from the audience. Actually, there are two, and I think they fit together. The first is, please explain why we can see the beginning of the universe in all directions. Shouldn't it have started in one place, not everywhere? And the related one is, can you tell where we are relative to the edge and center of the universe, the Big Bang? And if so, where are we?
I hate these. I've had this question many times. That's the reason I showed that particular diagram where the beginning is on the outside and the present is on the inside, is just to point out that the beginning was everywhere. And so if the universe is Euclidean, then it's actually infinite. And the only thing that happened is it's gotten bigger, right? It's infinite, and then it's 2 infinite, and then it's 3 infinite, and so on. It's, it's easy, right? You just and it gets more complicated if the universe is finite and still expanding. But the usual kind of example we give is there's not a preferred location on an ideal sphere. If you're confined to the surface of a sphere, every point is equivalent, right? And everywhere you do it. And so Alex I thought he was going to do the vector addition, but he didn't quite do it in time. But, all the places are equivalent when the universe is expanding uniformly. And so it is not clear there needs to be any center place for the Big Bang or any edge to the Big Bang. But even if there needed to be a finite universe, the universe doesn't have to have an edge. It can be a simple closed universe like a sphere where there's no edge. There's no edge to the Earth, right? You don't sail and fall off the Earth. You just keep going around it. And the universe could be pretty much the same way. So it's the kind of thing where it's great if you have a model and you can show, you can put up the model and show it, and you can realize that there is no necessarily a center of the Big Bang. We would have to be very special to be in the center of the Big Bang and have things going on. Although every now and then people come up with the crazy idea of trying to get rid of the dark energy by having us in the center of an expanding bubble, or near the very center of the, and you know, so every now and then people want to have us in a very special place, even though it looks like the universe is pretty uniform.
As we all know, the Nobel Conference is attended by a very diverse audience. I've got a kind of a unique question here. We all want to encourage our youth to be interested in science. I have a question here from Cassidy, who's age 5. And I have a suspicion a parent wrote it on the card. But Cassidy wants to know, and anybody can take this, I guess, how does a satellite move?
Oh, George. George, there you go.
All right, so I hate to do this because I'm used to teaching more advanced courses where we're trying to train them not to think about Newtonian gravity. But if you realize that this glass, if I let go of it, will fall to the table because of gravity, your own personal experience, there's a detraction of all the particles in the Earth, the glass. Likewise, there's an equal and opposite retraction of the Earth towards the glass. And so a satellite, if it's up in space, will be attracted towards the Earth. And so the only reason it stays in space is if it has a sideway velocity so much that as it's falling, it moves around the Earth in such a way that the falling just makes it follow a curve around the Earth. And so it's difficult to see. It's easy to see when you have an object on a string, that the force pulling on the string and the force of the thing trying to run away match each other. But when you don't have the string, it's gravity that's pulling, it's less obvious, but it's the same basic principle. There's a tendency for things to keep going the way they were going, and a tendency for them to be attracted. The combination will end up in a nice circular or elliptical orbit around Earth if you have the right conditions.
Professor Gates?
I have a question, not just for...
Oh, I thought you were going to answer the question better than I did.
Well, first of all, I think Frank answered that question yesterday.
Well, Newton did.
Well,
yeah, Newton did.
But yes, but you showed Newton's drawing. However, I actually have a question for the two Georges, not just for the single Georges.
Uh-oh.
To George S., as one of the people in the world who has been on the leading edge of bringing this sort of information to our species, how do you react to the fact that this science, when presented to many people, offends them? And that's partly why I want to get the other George in on this question.
Thank you.
We'll talk about it.
All right, so
George.
let me challenge your presumption first.
That's just fine.
It's my early experience was in general that almost no one was offended by learning about cosmology. They were amazed and thought the Big Bang was kind of stupid, but the fact that there was data and observations to back it up, they thought this is pretty incredible and pretty amazing, and that was a good thing. It's actually been in more recent times that much more conservative religious groups have started getting upset about that, and the same way they boycotted, there was a IMAX movie made showing these incredible fishes around the hot fence in the bottom of the ocean, which are clearly very different from any other fishes on the Earth, and clearly evolved, or in their case created to live in this unique environment. And so these groups organized boycotts to prevent that film from ever being shown because it's too visually compelling to make that kind of argument. So it used to be that it was only sort of evolution that people were attacking. But the fact that we're learning so much about the universe and the evolving universe, and that some scientists have dared to create the universe for nothing without even God, but it's a trend. There are waves in religions and ideologies and so we happen to be in one that way. And I'm always kind of surprised and so forth. And so if we had a lot more time, I would talk to you about the time I went to the Vatican for the trial. And one of the things in one of the talks, we had the break afterwards like that, and it was a scientists, astrophysicists, cosmologists, and theologians, and philosophers were there. So it was an interesting kind of thing. And the philosophers, and particularly theologians, were saying, we're worried that science has bypassed us and made us irrelevant to not irreverent, but irrelevant to whatever it was like that. And I started thinking about what it was, and I said, because clearly over time, many more people have worked on theology and many more people have worked on philosophy than they have on science. And yet science has made this tremendous rise in the last 100 years, and it has to do with that. And I thought, well, it's obvious. One of the scriptures we study is the world, right? And nobody else does, right? They don't look at the world and use it as a source the way we do, right? I mean, if you're limited to the Bible, you're much more constricted to where you can find new information and make progress. Whereas if you look at the world, there's plenty of new discoveries to be made. So young kids, you can do both.
I will talk about this in my talk today. I don't want to put it off, so I'll say a word now. At my talk today, I won't take up a second collection or anything, so don't even... I think that to approach your question, I don't know how widespread it is. It's widespread enough, namely the following. I have a lot of close, very devout religious friends, not just Catholic, but in Christianity in general, who pray that scientists will not find answers to certain questions so that they can continue to believe in God. Now that's pardon me, that's the damnedest, dumbest attitude. But it frankly has its source into a lot of religious people. God is a source of explanation. And she is not a source of explanation. If you are a religious believer, God is a source of love. I hate to use that word, but God is a source of love. And then only secondarily, but that's where the real problem is. So they feel science is a challenge to their religious belief because eventually there's going to be no need for God. Scientists will have the answers, and that may come. But it's the fundamental thing is God is a source of explanation.
Well,
that's the problem.
Many of the great classical scientists, including Galileo, Newton, Kepler, Faraday, Maxwell, all of them thought of what they were doing as discovering how God is manifested in the world, what God is, by studying God's creation. And I think that's the right attitude.
They not only did that, Frank, but they also, the foundings of modern science, I think it's well established, with Galileo, Leibniz, Descartes, on through Einstein up until today. But at least modern science was founded on a time when all of those scientists were religious believers, as you just said. But more than that, they tried to establish their religious belief on the same rational grounds that they had established their gravity and their... Newton's, the God of the gaps of Newton is well known.
Yes. Let me just jump in. George and I are, as I'll point out, are good friends, and he's a very wise man. But
until today.
No, absolutely. Frank is wrong, but that's a different question.
Before you start, Lawrence, I'd like to make another point, which I wanted to make yesterday, actually, but I wasn't alert enough.
Okay.
When we were talking about public support of science and what we could do, one thing that I think we should confront is look at ourselves in the mirror and asking what we're doing wrong and how we're presenting ourselves. And I think there are two outstanding things we're doing wrong. One is not presenting results honestly. When people oversell things, talk about theory of everything, put forward very speculative and even dubious ideas as great discoveries, this is very destructive. It undermines credibility that we need. And the other thing is being very aggressive and supporting a kind of theology that's thought of as anti-theology, but it is really a theology in its own right of aggressive expansion of the domain of science into ethics and morality, where it really doesn't have definitive statements to make.
Well, okay, so I agree with that, and we'll continue that discussion after my talk. So we must not present science for anything it isn't, and the limitation of science is very important. And so we all agree, but I want to just interrupt the love fest for a moment and say that
Are you looking at me?
Yeah, no. I mean, no. No, because what I was looking at you because you said something very sensible, which was that the friends of yours who hoped that scientists wouldn't discover certain things because it would end their faith. You're right, that's just the dumbest thing. But that's okay for them to be dumb. What's really, that's not dangerous. What's dangerous is when those same people don't want their children to learn what we now know for fear that they'll lose their faith. And that's dangerous.
Okay. No problem with that.
May I get into this just one more time? having set off this gentle discussion.
Yeah. Thank you.
This has been, as I've commented a number of times, I've spent time here at Gustavus, and one of the most rewarding things that has happened to me here, because this is a university, this is an institution that has a faith-based tradition. The Lutheran Church clearly played an important role here. And in teaching a course with my good friend here, Steve, a couple of years ago on this campus, one of our young students at the end of the course wrote an essay, and he was expressing his great gratitude and joy because he finally learned that scientists were not trying to prove nor disprove the existence of God. And I think this is the most important message that we scientists must get out to society.
And well, that's true. Although the point is, it's what most people, Steve Weinberg, who I think has been here before and I expect will come again, Nobel Prize winning physicist, has said something very important, which is that most scientists don't think enough about God to even know if they're atheists. God never enters into the discussions. And it's just irrelevant. It never, in all the years I've been at physics meetings, I've never heard the word come up. And so I think most people, this question of what we do what we sometimes mislead people to think when we have these discussions, as we are now, that somehow it's a central issue that scientists are concerned about. And it isn't. They're just concerned about trying to figure out how the world works.
As I said, neither prove nor disprove, right?
Yeah. Well,
we're doing something different.
I'll talk, I'm trying to hold my tongue because I want to talk a little bit about it.
I'm sure I'll discuss this with you then.
Yeah, we'll have another chance to discuss after my talk.
All right, and we shall break for lunch and reconvene at 1 o'clock for Professor Krauss.